Hi there. Today we'll look at symbolic knowledge distillation from general language models to Commonsense models by Peter West and others of the University of Washington and the Allen Institute for Artificial Intelligence. On a high level, this paper takes a new approach to symbolic knowledge generation, so to automatically coming up with knowledge graphs, with symbolic knowledge graphs, and rather than trying to mine this symbolic knowledge automatically from raw text or from existing knowledge bases, they mine it from GPT-3. So they use the GPT-3 large language model in order to first come up with a corpus that gives them a corpus of symbolic knowledge, and then they use that corpus in order to train a model that they call a common sense model, but essentially a knowledge graph completion model. So this is a new paradigm where you go, what they say, from machine to corpus to machine, and it is the paradigm they advertise here, in contrast to what people did before, the from human to corpus to machine, which is where humans generate a corpus and then you train the machine on that corpus. So we're going to look into how they do it. It's pretty surprising what they find in that, for example, the distilled model, the models they come up with at the end, they tend to be better not only than the humans or the human fed models, they even tend to be better than the original teacher, the GPT-3 teacher. And this is a result of how they combine the different elements here of the system, and they strategically bring in outside help in the form of human knowledge. So this could be a recipe for much more broad applications, not only knowledge graph generation, but various natural language tasks. They combine cleverly prompting, training small models, and as I said, bringing in small amounts of human annotated data strategically. So, as I said, we'll go through it, we'll look at the different stages, and yeah, tell me what you think in the comments, subscribe if you haven't, and let's dive in. But first, a quick word from our sponsor, Weights and Biases, your one-stop shop. If you're a machine learning researcher, practitioner, a hobbyist, a power user, it does not matter. Weights and Biases is with you from the inception of your idea, tracking your experiments, to really getting the fine details right, optimizing your hyperparameters, up until you deploy your model and track all of your metrics. Not only does it do that, it also organizes your datasets, your models, and you can generate super cool reports from all of that. In addition to that, it lets you have great insight into what you research and what you produce, and all of this runs in the cloud really effortless with a single line of code. Though today I want to talk to you about a yet not so well-known feature of Weights and Biases, and that is the Weights and Biases community. So I believe they recently migrated this from like a giant Slack onto this new sleek community website. It's a discourse-based forum essentially, where you can get help not only for Weights and Biases stuff, but also machine learning in general. But not only is it a help page, it's a discussion forum about all things machine learning. Also, they organize regular events, book reading groups, and paper discussions, and so on. So if you're interested, don't hesitate and hop over to the Introduce Yourself thread and take part in the discussion. As I said, this is still a pretty young place, but it's bound to grow over the near future. And of course, if you want any advice on Weights and Biases, how to use it, what the best practices are, this is the best place to do so. Thanks again to Weights and Biases for sponsoring this video. It's an awesome system. I invite you to check it out, and back to the video. So what's the deal with knowledge? I can't read this without pronouncing knowledge as knowledge. So what you want to do is you want to have symbolic knowledge. And in this particular case, the symbolic knowledge they're after is what they always have to have what they call an event and a relation. So an event, relation. An event, they give some examples, but essentially the event is some kind of situation that a person finds themselves in. It's common sense reasoning. So it's not like Napoleon was born in France or something like that. I don't even know if that's true, but it's not that. It's common sense reasoning. So the event is a person finds themselves in some sort of situation, or two people. It can be one or two people. Then the relation is some sort of, well, it's probably better we make an example. The relation is some sort of this. For example, this is the situation right here. X starts running. The relation is, these are predefined relations, and we deal with 7 different relations right here. These 7 relations are chosen because they represent sort of causal knowledge. One of them is effect, which means what is the effect of this event, or what is one possible effect of this event. And the goal of the model is to come up with this thing down here. So you prompt the model by saying X starts running. We have the effect relation, so the model is supposed to come up with the effect of starting to run. Now, there's not only one correct example, there are many correct examples right here, but one example is X gets in shape. This is not a direct logical, you can't prove it mathematically, right? Or you can't check it, and that's why it's called common sense reasoning. A human would look at this, says X starts running, is the effect of that X might get in shape? Yes, probably. So that is a valid triple. Okay, let's look at another one. Let's maybe take one with 2 people in it. No, there is none with 2 people right here. Let's see. X is not well liked. That is the event. The relation that we give to the model right here is the react relation, which means how does X react to that event? So X feels lonely. And that as well kind of makes sense, right? If you as a human judge this, you apply your common sense, makes sense. So I hope the task is clear. Given an event and a relation where the event can be anything, like anything involving X or X and Y, which are 1 or 2 people, and any piece of text, right? This is any piece of text right here. And the relation, they are 7 different predefined relations. You have to give the result right here, the inference. And the inference, again, can be any text. So this is quite a challenging task, right? And humans have come up with a data set for this task. I don't know where they describe it right here. They have come up with a data set called Atomic 2020. So the Atomic data set is a data set where humans go and humans make these triples, right? It's a data set made by humans as you would make data sets. This takes a lot of work, costs a lot of money, and we would like to have methods for not having to do that necessarily. So either to cut out the humans altogether or to use the human labor more strategically, such that it doesn't cost as much. And they also, the model that's trained on this human corpus, it's called Comet 2020. That is, if we simply feed the human corpus to a deep learning model, have it learn to predict the inference from the event and relation, that model is called Comet 2020, and that's going to be our baseline. And obviously, we're going to surpass that. So the result of this paper is going to be another corpus called Atomic 10x, which is 10 times the size of the human atomic data set, which is going to be better or larger and with appropriate filtering, also better in quality than the original corpus, which is surprising, right? And then also the Comet Distill model, which is the model that's trained on the Atomic 10x dataset, and that is going to be, as well, depending on the filtering, largely better than the original Comet 2020 model that's trained on human data. So that's the goal, that we get there. We get to a model that is better than it had we trained on human data. And along we get a corpus that is better than the human corpus. So again, the original paradigm was humans think with their brains, like here from the brain comes a corpus, right? So I invent a bunch of corpus entries, right? Maybe I let many humans do this. I come up with a corpus manually, then I feed that corpus to the model, to the machine. So there's a neural network right here. I train the neural network on that machine. Neural network thinks, yeah, cool. The new paradigm is the following. I take a big, giant neural network, such as GPT-3, that is not necessarily trained on this task, right? I'm going to make GPT-3 have one more layer than the other network to symbolize its absolute bigness. So GPT-3 is trained on the whole worldwide. Is this a globe? This is a globe. GPT-3 is trained on the whole World Wide Web, or at least readable part of it. And I'm going to use GPT-3 in order to come up with the corpus. Okay, so I'm going to use GPT-3 to come up with this corpus. And then optionally, I'm going to filter that corpus with a model that I train on human data. Okay. So this is where the human component can come in right here. Now, we're going to see how this happens, but the obvious effect of this is that the human no longer needs to come up with examples. The human simply has to rate examples in order for the filtering mechanism to get better, which is much easier, much cheaper, and we don't need as much, I guess. Maybe we do, but it's much cheaper for the human to rate than to come up with stuff. So we use GPT-3 to come up with a corpus, and then we use that corpus to train our model. So we're going to use the power of these large language models to come up with corpus. And of course, the magic is going to be, how are we going to do this? And the answer is clever prompting. So there's a bunch of math right here about knowledge distillation. I'm not sure. I guess they just had to put this in to get accepted, because you need like a bunch of math and yada, yada, yada. But essentially it's irrelevant. So yeah, sorry if you disagree, authors. But yeah, it's essentially irrelevant. So the key findings of the paper, actually we're going to skip this because we get this at the end. So what do we mean by clever prompting? We want to come up with a corpus. The corpus should have events. The corpus should have relations. The relations, of course, we know. The corpus should have inferences. So they have this general template for prompting GPT-3. They start off with a task prompt where you briefly describe the task inside the prompt. And then they have a bunch of examples. So the input, the output, the input, the output, the input, the output. And then they have another input, and this is the input they're actually interested in, and they're going to let GPT-3 complete the output right here. Now, given that they have the task description right here, and they have this pattern of repeating inputs and outputs, you can get GPT-3 to continue the pattern and actually give you what you want right here. We've seen this a number of times right here. This is called prompting or prompt engineering, and I predicted this right away when GPT-3 came out, that prompt engineering would sort of be like a quite an important thing to do in the future. So importantly, we don't train GPT-3, we simply query GPT-3 in a very structured way in order for us to create a data set, essentially. I think that's even against the terms of service of GPT-3, but they must have gotten an exception here. This paper is also cool because it finds a number of interesting things in prompting. Now, some of you might have been aware of this, others not, but there are interesting effects. For example, you want to number these things right here. You want to label them with actual numbers, such as that. They say this increases the degree to which GPT-3 follows previous examples. And also, when they construct examples, for example, like this, X goes jogging, they also say if they replace X and Y and so on by common names, it also works better. So you really want to, I think it's still a bit of an art form to see exactly how you have to phrase the things you put into GPT-3 such that you get out something good. So the first task they're going to do is they're going to create these events. Right? Ultimately, we want to create the data set, but the first step is we create the events. So they go to the atomic data set, this human-generated data set, and what they do is they simply sample. So they collect a set of 100 high-quality events from Atomic 2020 to use in our prompt. Note that, yes, they do make use of the human corpus right here, which is a little bit unfair when you think of comparing to that. But given that it is 100 examples, that is something you could still easily come up with, even as a researcher, right? Or you could pay a bunch of humans. 100 examples isn't that much. So we go and we collect 100, and then we simply, every time we go to GPT-3, we randomly sample 10. We put the 10 inside of the prompt, right? We simply list the 10 events. For example, X overcomes evil with good, X does not learn from Y, and so on. We simply list that, and then we put 11, and we let GPT-3 continue the prompt right here. And that here is going to give us a next event. I guess we could even let it continue more, but there are these issues like repeating and so on. So I'm not exactly sure how well that would go. But in any case, you can generate essentially infinity events, because even if you put the exact 10 same events in the exact same order, right? Since you sample with nucleus sampling, it doesn't give you the same results. Therefore, you can generate a lot of events. In fact, they generate 165,000 unique events, which is, as you can see, quite a bit more than the human authored corpus, which only has 6.2 thousand events. And all you needed as a base is 100 of these events, right? 100 were enough in order to create 165,000. That is the power of these large language models. You can essentially count on them already having built in all of this sort of language modeling, all of this, well, you might call it knowledge, or you might simply call it data that they have absorbed. But you can query that in a particular way. And the way we query it here, it gives us new events. All right, so this is the way, pretty simple, that we create new events. Now, from these events, we want to create these triples, right? The triples are going to actually make up the data set. So for a triple, remember we need an event, we need a relation, and then we need an inference. So the events we now have, check. The relations, there are just 7 of them. They're always the same in this data set. So we have them as well. So now we can simply take an event from the data we created, pair it with a relation, and then we have to come up with an inference. And again, we're going to use clever prompting and GPT-3. So what the authors do is that for each relation, they come up with a textual representation of that relation. So by the way, the relations are described right here. There is X adder, how X is perceived after an event, how X reacts in response to an event, what effect does it have on X, what was X's intent in event, and so on. So these are the kinds of relations that we're dealing with right here. They give an example here for the need relation, which is here what X needed for the event to happen. And their textual representation is as follows. So I'm going to put the event with an event number right here, according to what they said at the beginning. It helps when you number the individual entries. Then they're going to write prerequisites for this to happen, comma, and then the actual inference goes here, right, until here. So they're going to repeat this. This is 1. They're going to repeat it 2, 3, and so on. Again, they're going to put 10 samples into the prompt with the inference filled out. And then for the 11th one, they're simply going to put the event right here and the prompt that they have already used. And then they're going to let GPT-3 fill in the rest right here. And that thing is going to be the GPT-3 provided inference. So, they say, as in 3.2, we sample 10 few-shot examples for each prompt from a set of 100 human-authored cases. For each pair of event and relation, we generate 10 inferences with the second largest form, following the same hyperparameters as event generation. Now, they don't use the largest form of GPT-3 because it would cost them too much money. So they use the second largest one. But you do the same thing. You generate just very, very, very few human-authored cases. So that's 100 human-authored cases. And I don't know if that is 100 per relation or just 100 in total. I don't know. I'm going to guess maybe per relations. I don't know. It doesn't say. It just says we replace anonymous names with generic names as this improves quality. However, it doesn't matter if it's 100 or 700. It's still very, very few compared to having humans come up with an entire corpus. So what you want to do is you simply want to give GPT-3 a little bit of input, like 10 different things of input, and these 10 things you may vary a little bit over time. You might not even have to. And let's not forget the task description up here. That also seems to be important. And then they come up with 165,000 times 7 inferences, which you can filter a little bit, but in the end, this results in 6.46 million atomic style data triples. They call it atomic 10x, as it contains an order of magnitude more triples than the atomic 2020 with respect to the 7 relations they investigate. So this is a giant corpus right now of machine-generated data. I'm trying to find table 1 where they compare the size right here. Okay, so here you can see just the comparison of what that cost. You can see the total count in atomic 2020 is 600,000 triples, and atomic 10x has 10 times more triples, yet cost only a fraction of what atomic 2020 cost. Now the question is, of course, is this data set any good? This here at least has been generated by humans. Humans aren't perfect, but at least they have some common sense. Therefore, for a common sense data set, it might be important. Does the atomic 10x data set, is it any good? And that's what they go about investigating right now. So they evaluate the generated common sense knowledge graph. So they evaluate now these triples. First of all, they look for diversity. So they have a few diversity-related metrics, such as like hard diversity, or this what they call blue soft uniqueness, where they check for overlap between the triples and look how many of them are unique. They also try to train a GPT-2 model and look at the entropy of the different data sets. And in general, they find that the machine-generated data is quite diverse as quite high entropy. So there's not much of a problem right there. It's also quite unique. It is not as unique, it seems, as the human-generated data, but given that you have so much more of it, the absolute number of unique things is way, way higher. The real kicker comes when you do actual human evaluation. So they have spent a lot of time into humanly evaluating the quality of whatever they produce. The humans have been asked to rate these triples into, for example, always, often. So when you see an event, a relation, and an inference, you as a human have to say, does this inference always or often come from the event and the relation? Is it sometimes? Is it likely? If you said one of the two, it would be accepted. The triplet would be counted as good. If you as a human say, that's kind of far-fetched, or that never happens, or is invalid, then you would reject the triple. If you look at this, then you can see right here, in the human-authored dataset, the humans accepted 68% of the triples and rejected 11%. Whereas this top row right here is the unfiltered dataset we got from GPT-3 with the prompting, and you can see that the accept probability is slightly lower, actually quite a bit lower, like 8% lower. And the humans also reject more often, and even sometimes not available means that you can't make any judgment on it. So the number it's way larger, right? But it's a bit lower in quality as assessed by humans, as it seems. So now they gear up. They say, okay, can we make this better? And their answer is yes, by introducing a critic. So making the teacher model more critical, where they go about the following. They have this formula right here. Maybe that math isn't as useless after all. So if you simply generate language, you simply have GPT-3 be a model, a probabilistic sequence model, a language model that simply says, what is the probability of the next token? And I'm going to sample by that probability. But now what you can do is you can introduce a critic. So if this is your language model, you can introduce a critic. And the critic also will have an opinion on how likely a particular sequence is. So now you consider both. You generate data with GPT-3, and then you let a critic evaluate that data, which essentially amounts to multiplying the two probabilities. But in practice, you would simply run the critic on the data, and then the critic decides, is this data good data or bad data? And that together, GPT-3 and the critic, you hope that they will produce a better data set than just GPT-3 alone, because now the critic is able to filter whatever GPT-3 says and only let the good data pass. Note that I think it's maybe the critic is probably capped at 1 or something like this. So this is a filtering mechanism. It's not like you can introduce new bad data. So we would expect that the filtered corpus is hopefully better. The question is, how much better is it? Okay, so now we introduce this critic, and the critic is where we strategically bring in human data. So the critic would remove unacceptable knowledge. In practice, this means filtering the generations in the large corpus and creating a range of new corpora that are higher quality, yet still larger scale than the human authored one. So for this, they gather a training set of correct versus incorrect human judgments on a randomly sampled set of 10K entries of atomic 10x. So they take their large corpus, they take 10,000 entries of it, and they let humans rate those 10,000 entries, much like they did here for the evaluation. Right? But this now goes as training data for the critic. And that's where I said we strategically bring in human knowledge. And not only do we strategically bring it in, rather than letting humans generate the entire corpus, we also make it easier for humans, because this isn't coming up with examples. Coming up with examples is hard, it takes time. These humans here, they simply need to read examples of the corpus, these 10,000 examples, and for each one they have to rate it. And this can even be noisy. So other than in the evaluation, where I think they gather 3 labels per data set, they say we only gather 1 annotation for each example. So this can be noisy since it's training data. And yeah, that seems to be quite a good way of thinking about human labor in machine learning. It's sort of, where can we bring it in to make the biggest difference? Now, when they do that, so they argue this here, it's vastly cheaper than human construction. Instead, we argue that a more useful and efficient role for humans in knowledge graph construction is to correct the mistakes of the teacher by evaluating a small number of examples. So they train a Roberta large model on the human annotated data as the critic. The critic, of course, doesn't have to be a language model. It doesn't have to generate anything. It simply has to look at the data and decide, is it good or is it not good? So they train that, now we go back to the table right here. These here, as we go down the table, more and more filtering is applied by the critic. So now you have a choice as a designer, right? You have this critic model. It tells you about how good a particular sample is, and now you get to decide the cutoff. You know, how much do I want to filter this data right here? Now, this will have a trade-off. The more you filter, the smaller the resulting data set is going to get. So we can look at a few examples. For the first step, you go from 5.6 million, from 6.5 to 5.1, which is a reduction in somewhere between somewhere on the order of 20% of data. So you throw away 20% of data. Look at that, the accept percentage jumps from 78% to 88%. So now human raters rate these triples in the corpus that you generate and then filter as more likely, more acceptable than the corpus that was authored by humans. Like, this is this is astounding already, right? Now, there might be a little bit of an effect here in that probably the humans that rated were the same humans, or at least, you know, humans from the same population or distribution than the humans that rated the training data for the critic, and therefore all of these humans might sort of have the same taste, whereas the humans that came up with the Atomic 2020 dataset might be, you know, different humans. I'm not sure, but it is astounding. And even more astounding, as you filter more, you can clearly see the accept percentage, therefore the quality of the data set going up. And to the point where you keep about 40% of the data that you've generated from GPT-3, yet the accept percentage is like 96%, which is like 10% higher, 10 percentage points higher than the accept percentage of the human generated data, right? This is quite astounding, and still you have like 4 to 5 times more data than the human created corpus. And they do some evaluation also, again, on the diversity of the data. And it actually turns out that as you filter more, the diversity increases. So that would be the relative diversity, meaning sort of how many percent of the data are, you know, different from other, how are unique, and so on. So it appears to be that GPT-3, when it just creates data, it will create a lot of good stuff, but also some garbage. And as it turns out, the garbage seems to be always the same kind of garbage. Therefore, if you filter out the garbage, also the uniqueness and diversity of your overall data set increases. So it's quite the opposite of, you always hear this, no, I guess it's that, this saying that was it all unhealthy families are the same, or all healthy ones? I don't know. But in this case, all the garbage GPT-3 produces is kind of the same kind of garbage, or the same few types of garbage, whereas all the good stuff it produces is relatively unique. All right, so now we have a really, this is what gets filtered out right here. So first of all, logical misalignment consists of events or inferences joined in a logically inconsistent manner. Well, that makes sense that gets filtered out. X cannot find his shirt. As a result, X is wearing a shirt. Yeah, that should probably not be in there. And two, awkward phrasings, which consist of events or inferences that in isolation are incoherent, ambiguous, or awkwardly phrased. So when an event itself is already poorly phrased, the model essentially has no chance of generating a good inference. Like, person X has a fire in the bath. Yeah, so there is just there's a high chance that a human would negatively rate this, or not accept it, or say it not available. Even like from the get-go, doesn't even matter what the relation and the inference is, right? So the last step is we want to go back to a model. So we have taken GPT-3, a model. We have used it strategically to come up with a corpus that is both better in quality, more diverse, and larger than the corpus that humans have generated. And now we want to go back to creating a model from that corpus. So I want to train an inference model, because right now we can only generate data, but we would like to have an inference model. And remember the original task, the inference is to, given an event and a relation, to produce an inference, right? Which you could do with GPT-3, but it's sort of not super good. So you have to filter with the critic, but that means you have to like sample until the critic says it's okay. What you'd rather have is you'd like to have a model that is trained on this data to produce directly the inference, rather than having to prompt GPT-3, right? So the model can be way smaller than GPT-3 because it's directly trained on the task, and you don't have to pay OpenAI every time you call it. So now I want to go back to a model, and that's pretty easy, right? We simply take the same architecture as this Comet model. Remember, the Comet model is the model that's trained on this human data to do this inference. Simply take same architecture, and we train it on the large corpus. And you know what turns out? So it turns out that we do that, and then we let again humans rate the triples that the models produce. So for the Comet 2020, this is the model that's trained on the human corpus. This here you can again see the accept percentage by the raters of the corpus itself. When we train the model on it to do this inference for us, the model produces triples that get accepted 81% of the time, which is pretty good, right? So if the corpus gets accepted this much, we train a model on it, an NLP model. It's pretty good to drop only a little bit in the accept percentage. That means the model has essentially learned, because this is obviously on a validation set. The model has obviously learned to do this inference somewhat correctly. Now, if we do the same on our large corpus, that has lower accept percentage, we see the same effect. So the model kind of learns. In fact, overall, we see the same effects. If we now add a critic with a low threshold, then we surpass already this model. And if we add a critic with the high threshold, so that would correspond to throwing away 60% of the data, as we saw before, then the model that we end up with has an 87.5% accept rating. So now we have a model that's the same size as this Comet 2020, right? It is a trained model. It's not GPT-3, it's not prompting, it's a trained model that does inference in these triples, and it is better than the same model that's been trained on the human corpus, which is pretty cool, right? So it not only does it surpass GPT-3 itself, it also surpasses the human generated data, and yeah, that's pretty cool. So this was essentially the findings of this paper. I guess we can go back to conclude with what they said at the beginning, the key findings right here. Learning symbolic knowledge from language models can be framed as a symbolic extension to knowledge distillation. Okay, so that's the mathy part. Symbolic knowledge distillation constructs a high quality knowledge graph at scale. Okay, that's their data generation process. A critical teacher results in a higher quality student. Granted, the critical teacher makes the quality of the data set better, and therefore any model, the student that is trained on that data set, it will become better. A notable ingredient right here is that here is where we actually bring in the human annotated data into this process of automated knowledge graph generation, because we need to train that critic. Critical teachers or not, a student can outperform the knowledge source. So this is about that the student model, they exceed the quality of GPT-3, which, so if you simply prompt GPT-3, you get some of these triples, right? Yet the student models that are trained on these triples that come from GPT-3 outperform GPT-3, which can make sense since GPT-3 is a general purpose language model and these student models are specifically trained on that particular kind of data. And also, I have to say the student models, they're GPT-2. So in the student model, what you would do is you have your corpus, you have event, relation, inference, right? These are your samples. This is all text essentially, right? So the relation, you can abstract that in either a single token or you can make it into a text as they did. So they feed that into a GPT-2, which is something that you can train. And that GPT-2 is trained to take in an event and a relation into the context and then generate the inference, much like GPT-3, but now you actually train it specifically on this particular data structure and data set. And the GPT-2, you pre-train it, of course, on language modeling. And it could be that some of the effect that the student's model exceed the quality of GPT-3 might be due to the fact that it starts out already from a GPT-2 checkpoint. There's a possibility that also plays into the game right here. Machines can now win over humans for automatic knowledge graph construction. So that is a little bit shady, since the critics you train are still using humans. But I would agree that at least the paper shows that there are better places to use human knowledge than letting humans come up with a text corpus, because these text corpora can be generated pretty easily using large language models and proper prompting. And if you do that, then you can use the human knowledge to filter whatever the language models output, and that might be much more effective. So this was it for this paper. I hope to not only show this paper, but give you a little bit of an idea of what all is possible with these language models and proper prompt engineering. And I think this serves as a little bit of a recipe for many or a lot of things to come. A lot of NLP tasks to be done could be tackled in this particular way. All right, so yeah, let me know what you think in the comments, and bye-bye.